Welcome in. Our goal for this video is to perform stoichiometry calculations using balanced chemical reactions. We can think about our chemical reactions like recipes. The information in our balanced reactions is exactly the same thing. How much of each ingredient do you need, or reactant, and how much product can you make when you combine those things? Just like recipes, we can scale up or scale down. If you're feeding just one person, you can cut a recipe in half. If you're feeding a large group, you can double or triple or quadruple a recipe, or somewhere in between. If you are adjusting one amount in your recipe, in your reaction, you need to adjust all the other amounts accordingly. Here we have my recipe for the perfect pizza. You need exactly half a pound of dough, half a cup of pizza sauce, 3/4 of a cup of cheese, and with that you can make one pizza. If this is our recipe, but we're cooking for, a bigger group, we can decide, okay, how much dough is required to cook 3 pizzas? Or how many pizzas can we cook if we have 4 cups of cheese? The idea is we can do the same dimensional analysis that we've done in the past. If we need to make 3 pizzas, we can cancel out pizzas, and get to dough. In order to figure out this conversion, we want to look at our recipe. Well, every 1 pizza requires half a pound of dough. So we can put those numbers into our conversion. Great. If you want to cook 3 pizzas, you need 1.5 pounds of your pizza dough. The second example, if you have 4 cups of cheese, we can try to cancel out cups of cheese and end up with maybe pizzas. Again, we can look at our recipe. Every 1 pizza requires 3/4 of a cup of cheese. With this much cheese, we can make just over 5 pizzas. Getting back to chemistry, it's less tasty, but our chemical reactions get to work and behave the exact same way. Our coefficients in our balanced reaction are exactly telling us those relative amounts. For every 3 of these hydrogen molecules, we need 1 of our nitrogen molecules. Or for every 3 of our hydrogens, we get to create 2 of our ammonias. These reactions, the ratios, it works in terms of molecules. It's also going to work in terms of moles. Moles is going to be more useful because that is going to be our home base. That is where we can get to easily from any other unit in terms of our conversions. Our question down below, if we have 3 moles of nitrogen and we don't care about moles of nitrogen, but we want to figure out the moles of our ammonia, we can look at the conversion. 1 of our nitrogen, N2, gets us to build 2 of our ammonias, NH3. We have a practice problem. If you have 3.4 moles of chlorine, how many moles of sodium chloride can be produced? Grab your paper, grab your pencil, try to write down that good answer. For more complicated problems, we might need to do more than one step in our conversion, though. In general, in our course, almost all of our calculations can be summarized in the same 3 steps. We like to get to moles first because that is our home base. That is our central hub. Once you convert to moles, you can convert to the chemical or element that you care about using our balanced reaction. Once we have the chemical we care about in units of moles, we can convert to whatever final unit that we want. So far, we've talked about molar mass as a way to get to moles, and we've used Avogadro's number as a way to get to moles. We're going to just add more ways to get to moles throughout our course. Likewise, once we're in units of moles in the right chemical, we can use molar mass to convert back to grams, or we can use Avogadro's number to convert to the amount of something. Here's an example. We know we have 100 grams of magnesium hydroxide. We want to calculate how many grams of hydrochloric acid must react with it. If we're building up a map, our first step should be convert to moles. We're given grams of magnesium hydroxide. Let's convert that to moles. Our second step can be to convert to the chemical that we care about. In this case, they're asking us about HCl. Let's convert over to HCl instead of MgOH2. Lastly, we're asked in units of grams, not in units of moles, so we can convert over to grams of HCl instead of moles. This first conversion we can set up canceling out grams, getting to moles. If we have 1 mole of this magnesium hydroxide, how heavy is that? We need to use the periodic table to find our molar mass. Our second step, we don't want magnesium hydroxide. Instead, we want HCl. This is our new one. We need to look at our balanced reaction. According to our reaction, we have 2 HCl's for every 1 of our magnesium hydroxide. Lastly, we can cancel out moles of HCl and try to get grams of HCl. If you have 1 mole of hydrochloric acid, this is going to correspond to, well, how heavy is this? This is, again, a molar mass calculation. About 36.5 grams for every 1 mole. And there we go. We should react 125 grams of our HCl with our 100 grams of MgOH2. We have a practice problem. See if we can set this one up on our own. Grab some paper, write down that good answer. And again, more repetition is better. Here is another practice problem. See if you can get the answer to this one. We want to introduce one more way to do our stoichiometry calculations, and that is by measuring the heat involved in our reactions. Previously, we talked about heat as energy exchanged when changing the temperature of an object, and we used our favorite heat equation, Q equals mc delta T. This is great if there are no chemical reactions occurring. This is using heat to change the temperature of an object, but it does not account for heat exchanged during our chemical reactions. So, if we are performing chemical reactions, we need to have a new method for calculating heat. Our new method uses a concept known as enthalpy. Enthalpy, given the symbol delta H, is the amount of heat transferred during a chemical reaction. This delta H is a numerical value, and it's associated with a balanced chemical reaction. Here are some examples. We have methane combusting with oxygen, and our enthalpy for this reaction is negative 802.3 kilojoules. This negative sign tells us that our reaction is exothermic, that energy is being produced during this reaction. A second example, nitrogen and oxygen combined to form two nitrogen monoxides. In this reaction, 182.6 kilojoules of energy is absorbed during this reaction. These thermochemical equations are balanced and have our delta H value written to go with that balanced equation. This top reaction says 1 mole of CH4, that is methane, produces 802.3 kilojoules worth of energy. Likewise, if you combust 2 moles of oxygen, you're also going to produce 802 kilojoules of energy. Or when we create 1 mole of CO2, we create 802 kilojoules worth of energy. Or when we create 2 moles of water, we also create that much energy. So if you have 1 mole of CH4, that is going to correspond to negative 802.3 kilojoules. If you have 2 moles of CH4, burning twice as much fuel is going to produce twice as much energy. If you have 3 moles of CH4, you're going to produce triple that amount of energy compared to our written out delta H value. We can codify this using conversion factors. Conversion factors can be built using our enthalpy value on half of our fraction and using the coefficient from the balanced reaction on the other half of our fraction. So for example, here's a new reaction. If you're thinking about the enthalpy for C3H8 combusting, we can build a conversion factor using our moles of C3H8 and our enthalpy for the overall reaction. If we care about oxygen instead of C3H8, we can make a different conversion factor using oxygen instead. If we care about CO2, we can build that conversion. If we care about water, we can build that conversion. Because our reaction is balanced with that delta H in mind, you can use the coefficient and the number for delta H to build whatever conversion factor that you want. Any of those chemicals can be related to our delta H value. These conversions are useful. It allows us to convert from heat to the number of moles. Or put another way, we have another tool to get to moles in our 3-step calculation. Not just molar mass and Avogadro's number, but now we can also use the heat of our reaction or the enthalpy of our reaction. At the end of our steps, we can use the molar mass, Avogadro's number, or that value for delta H. In the middle, we like to use our balanced reaction to convert from one chemical to another. We're just adding on a tool we can use in the beginning or at the end. We can do an example here. If we have 155 grams of ammonia, we can try to calculate the heat associated with the complete reaction of 155 grams ammonia. Our first step can be to get to moles of ammonia. Once we have moles, we can use our delta H to get to kilojoules of heat. Step 1, we want to cancel grams and get to moles. If we have 1 mole of ammonia, how many grams is that? How heavy? This seems like a molar mass calculation. Nitrogen plus 3 hydrogens. Our second step, we want to figure out the amount of heat. Since we're doing heat of a reaction, this has to be delta H. We can take our coefficient and put it in half our fraction. We can take our delta H and put it in the other half of our fraction. The delta H has to go with our kilojoules, and our moles has to go with our coefficient. Negative 2060 kilojoules worth of heat. Negative means that this is being produced. For practice, we have a problem here about butane required to produce this many kilojoules of heat. Grab your paper and pencil, try to write down those good answers. There we go. We've introduced our plan for doing stoichiometry calculations using our balanced chemical reactions to convert from chemicals to different chemicals. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.